Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can slowly unwind and knowledge becomes a soft companion for the night. Tonight, our journey takes us far beyond the stars, beyond the galaxies mapped by telescopes, and perhaps even beyond the limits of what any human being could ever observe. We're going to explore what may lie outside the observable universe, and why modern physics suggests that most of reality has always been hidden from us. But before you settle in completely, I'd love if you could take a quiet moment to like this video and subscribe, only if these gentle explorations bring you some comfort or wonder, and if you feel like it, leave a comment letting me know where in the world you're listening from, and what time it is there right now. It's always strangely beautiful to imagine so many people scattered across Earth, all looking into the same universe from different corners of the night. Now, dim the lights a little if you'd like. Maybe let the room become softer around the edges. Perhaps there's the distant sound of a fan, or rain somewhere outside, or the quiet hum of a sleeping city, and together, very slowly, let's begin. Right now, at this exact moment, you're sitting inside a sphere almost unimaginably large. Not a physical sphere with walls or edges, but a sphere made from light and time, everything you can see in the night sky, every star, every distant galaxy, every ancient flash of radiation crossing space exists inside this enormous cosmic bubble surrounding you in all directions. Scientists call it the observable universe, and even that phrase feels strangely humble once you understand what it means. The observable universe contains something close to 2 trillion galaxies, not stars, galaxies, vast islands of stars, dust, black holes and planets drifting across darkness like glowing cities on a midnight ocean. The Milky Way itself may contain hundreds of billions of stars, and yet the Milky Way is only one ordinary galaxy among trillions more. If you tried counting those galaxies one by one, without ever sleeping, without ever pausing, it would take longer than recorded human history just to finish the task. And still, according to nearly everything modern cosmology tells us, this enormous visible universe may only be a tiny fragment of what actually exists. That is the part most people never hear. When documentaries talk about the size of the observable universe, it often sounds final, complete, like we have somehow mapped everything there is to map. But the observable universe is not the whole universe. It is only the portion whose light has had enough time to reach us since the cosmos became transparent long ago. In other words, what you see depends not only on what exists, but on what has been able to communicate with you through space and time, and that distinction changes everything. Imagine standing alone in a vast dark ocean at night with only a lantern in your hand. The circle of light around you may feel enormous compared to your own body. It may reveal waves stretching outward in every direction. But the edge of that light is not the edge of the ocean. It is only the edge of what the lantern allows you to see. The observable universe is something like that, a softly illuminated circle in a much larger darkness. What lies beyond that darkness is one of the deepest questions science has ever asked. And strangely, the more carefully physicists studied the universe, the more they began to suspect that the hidden regions beyond our cosmic horizon were not hidden accidentally. Not because our telescopes are weak, not because technology is unfinished, but because the universe itself may be structured in a way that permanently limits what any observer can ever know. That idea is difficult to absorb at first because human beings naturally imagine boundaries as physical things. A wall, a door, a mountain blocking the view. But the edge of the observable universe is not made of matter. There is no giant shell floating in space, no cosmic barrier waiting somewhere beyond the galaxies. The boundary is made from causality itself, from the simple fact that information travels at a finite speed. Light takes time to move across space, and space itself has been expanding since the beginning of cosmic history. In some regions, space expands so enormously, so relentlessly, that light emitted there can never fully catch up to us. Not in billions of years, not even if the universe survives for trillions more. Those regions still exist. Galaxies may shine there, stars may rise and fall there, entire histories may unfold there, and we may never know them directly. The universe, in a sense, contains places forever outside our conversation. That realization changes the emotional feeling of the night sky, because when you look upward now, you are no longer seeing everything. You're seeing a local window, a nearby patch of a structure that may extend vastly farther than human intuition comfortably allows. And the truly strange part is this: the same physics that allowed galaxies to form, the same ancient processes that eventually led to planets, oceans, chemistry, and living minds, may also be the reason most of reality became unreachable in the first place. The universe did not merely grow large, it grew in a way that hid itself. Modern cosmology increasingly suggests that hiddenness is not a flaw in our understanding. It may be woven directly into the architecture of spacetime itself, and tonight, slowly and carefully, we're going to follow that idea outward. We will explore why space appears almost perfectly flat across unimaginable distances, why the early universe expanded faster than anything should reasonably expand, why invisible horizons divide reality into reachable and unreachable regions, and why distant galaxies are gradually disappearing from the future universe forever. We will wander through the strange possibility that space may wrap around itself like a looping hallway without edges, and the even stranger possibility that our entire observable universe may be only one bubble among many, drifting inside a far larger cosmic structure. But for now, before all the equations and theories and horizons begin unfolding around us, it is worth pausing for one quiet moment beneath the simple fact itself. You are alive in a universe so large that even the visible part contains trillions of galaxies, and physics suggests that most of it lies forever beyond the horizon, not hidden behind distance alone, hidden behind time, hidden behind expansion, hidden inside the structure of reality itself, and yet somehow, from one small planet orbiting one ordinary star, the universe has begun trying to understand its own hidden shape through conscious minds like yours. That may be one of the strangest things of all. If you could somehow step far enough away from the universe to see its overall shape, what would it look like? It is such a strange question that the mind almost resists it at first. After all, we're used to shapes belonging to ordinary things. Apples have shapes, mountains have shapes, oceans and clouds and leaves have shapes. But the universe itself feels too large to imagine as a single object, too vast to hold in one picture. And yet, modern cosmology quietly suggests that the universe does have a geometry, not the geometry of individual galaxies or stars, but the geometry of space itself. For a very long time, physicists were unsure what they would eventually discover. Some imagined the universe might curve inward on itself like the surface of a giant sphere. Others wondered whether space might stretch outward endlessly in a kind of cosmic saddle shape. Still others suspected the universe could be perfectly balanced between those possibilities, neither curved inward nor outward in any dramatic way. And remarkably, after decades of observation, that last possibility appears to be the closest to reality. As far as scientists can measure, space is almost perfectly flat. Now, that statement sounds simple enough at first, almost disappointingly simple. Flat does not sound mysterious. It sounds ordinary, calm, maybe even boring. But in cosmology, flatness is one of the strangest discoveries ever made, because a flat universe is not a naturally stable thing. Imagine trying to balance a pencil upright on its tip. You might succeed for a fraction of a second if your hands are incredibly careful, but the tiniest movement would send it falling. A breath of air, a slight vibration, even the movement of your own heartbeat through your fingertips would be enough. The universe behaves in a surprisingly similar way. If the early cosmos had contained just a little too much matter and gravity, expansion would eventually have slowed, stopped, and reversed. Space itself would have collapsed inward over time. Galaxies would rush back toward one another. Temperatures would rise. The cosmos would fold inward like a wave curling back into the sea. On the other hand, if the early universe had expanded only slightly too quickly, matter would have spread apart so rapidly that galaxies might never have formed at all. Stars would never ignite. Chemistry would remain thin and scattered. The universe would become a cold, drifting fog, endlessly thinning into darkness. Life, in either case, would almost certainly never appear. And yet somehow, our universe seems balanced, almost exactly between those extremes, not dramatically collapsing, not violently dispersing, but unfolding slowly enough for stars to burn, planets to cool, oceans to form, and conscious beings to emerge billions of years later beneath quiet night skies. This balance is what cosmologists call the flatness problem. Not because flatness itself is bad, but because it seems astonishingly unlikely. The more carefully scientists studied the equations describing cosmic expansion, the stranger the situation became. When they mathematically rewound the history of the universe backward toward its earliest moments, they discovered something deeply unsettling. In the beginning, the balance had to be even more precise than it is today. Not slightly more precise, impossibly more precise. The early universe appears to have been balanced so delicately that even unimaginably tiny differences would have changed cosmic history completely. It is difficult to find human comparisons large enough to make the scale feel real. It would be like balancing a marble perfectly at the peak of a mountain during a hurricane and having it remain balanced for billions of years, or placing a pencil upright on a moving train, crossing an ocean during a storm, and finding it still standing at the end of the journey. The universe should have drifted away from flatness long ago, and yet it did not. That realization quietly troubled physicists for decades, because science is often comfortable with surprising outcomes, but it becomes uneasy when nature appears unnaturally fine-tuned without explanation. The cosmos looked less like something that casually settled into balance, and more like something balanced with impossible care. Some physicists even described the universe as resting on a knife edge. A little too much gravity, collapse, a little too much expansion, emptiness, and somehow reality threaded the narrow path between them. By the late 20th century, this puzzle had become impossible to ignore. Observations of distant galaxies, ancient radiation, and large-scale cosmic structure all pointed toward the same uncomfortable conclusion. The universe was far flatter than it had any obvious reason to be. Then, slowly, a possible answer began to emerge. It arrived not from astronomy at first, but from particle physics. From scientists trying to understand strange properties of the very early universe, long before galaxies existed, long before atoms fully formed, when reality itself may have behaved more like a sea of energy than a collection of objects. And the proposed solution was extraordinary. According to this idea, the early universe experienced a brief moment of expansion so violent, so unbelievably fast, that it stretched space itself beyond ordinary comprehension. Not expansion in the familiar sense, not galaxies drifting apart gently over billions of years, but space expanding explosively in less than the smallest fraction of a second imaginable. A tiny microscopic region, smaller than anything human beings could ever directly perceive, suddenly swelling to enormous size almost instantly. And that expansion, according to the theory, would naturally smooth and flatten the universe. A curved surface stretched large enough always begins to appear flatter locally. You experience this every day on Earth without thinking about it. The planet beneath your feet is round. But because Earth is so large compared to your body, the ground feels flat as you walk across it. Only from far away does the curvature become obvious. Now imagine stretching something vastly larger than a planet, stretching space-time itself until every wrinkle, every bend, every trace of curvature becomes almost impossible to detect. That was the insight, and with it, the universe began to look different. Not simply large, not simply expanding, but transformed by an ancient event so extreme that it reshaped the geometry of reality itself. Yet as elegant as this explanation seemed, it carried a strange consequence hidden quietly inside it. Because if the universe expanded that violently in its earliest moments, then the regions we can observe today may represent only a tiny surviving fragment of a vastly larger structure. This same process that flattened the cosmos may also be the reason most of it vanished beyond our reach forever. As the strange balance of the universe begins to settle into the imagination, another question naturally appears beside it. If inflation truly happened, what exactly was it? What could possibly cause space itself to expand so violently that the geometry of the entire cosmos would be permanently altered? To approach that question gently, it helps to forget galaxies for a moment. Forget stars. Forget planets and black holes and human beings sitting quietly beneath bedroom ceilings at night. Travel backward far enough in time, and the universe becomes something almost impossible to recognize. No galaxies yet drift through darkness. No atoms orbit silently in empty space. There is only an unimaginably hot and dense state, where energy fills everything like a blinding ocean without shorelines. And somewhere within that ancient state, according to modern cosmology, reality briefly entered a phase unlike anything we experience today. A phase where space itself began expanding faster and faster, not exploding outward into pre-existing emptiness as fireworks burst into the air. That image, although common, is misleading. Inflation was not matter flying through space. Inflation was space itself stretching. Every distance growing larger at once, every region carried away from every other region as the fabric of reality rapidly unfolded. The speed of this expansion is difficult for the human mind to comfortably absorb because nothing in ordinary life resembles it. Even the fastest things humans have ever built move slowly compared to the scale involved. Inflation did not simply enlarge the universe, it magnified it catastrophically. Some physicists compare it to a tiny speck swelling larger than entire galaxies almost instantly. Others describe it as reality doubling in size again and again and again in fractions of a second so brief that language begins to fail. Imagine drawing two tiny dots on the surface of a balloon. As the balloon inflates, the dots move apart. Not because the dots are crawling away from each other, but because the surface beneath them stretches. Now imagine that process becoming unimaginably extreme. The balloon doubling in size over and over faster than thought itself. Tiny distances becoming enormous almost immediately. That is the basic intuition behind inflation, and strangely, This violent expansion may explain why the universe appears so calm today, because inflation acts like a cosmic smoothing process. Wrinkles flatten, irregularities stretch thin, curvature fades. A useful image is bread dough rising in an oven. Before baking, the dough may contain folds, bumps, and uneven textures, but as it expands, those imperfections spread outward and become less noticeable across the larger surface. Inflation, according to the theory, did something similar to spacetime itself. It stretched the universe so enormously that any original curvature became nearly invisible from our local perspective. This elegantly solved the flatness problem that had troubled cosmologists for decades. But inflation also solved another mystery, one perhaps even stranger. When scientists first mapped the ancient radiation left over from the early universe, the faint glow, now called the cosmic microwave background, they discovered something astonishing. Regions of space separated by enormous distances had almost exactly the same temperature. This was deeply confusing. Those regions were so far apart that light itself should never have had enough time to travel between them. In principle, they should never have exchanged information. They should have evolved independently, like isolated islands with separate climates. And yet the temperatures matched almost perfectly. It was as though distant regions of the universe somehow knew about one another long before galaxies formed. This became known as the horizon problem. Inflation offered a graceful solution. Before inflation began, the universe may have been small enough for all regions to interact closely. Temperatures could equalize naturally, while everything remained compressed together. Then inflation suddenly expanded that tiny connected region to enormous size, carrying once neighbouring areas vastly beyond each other's horizons, like dots painted close together on a balloon before it expands. What appears disconnected today may once have been intimately close, and with that realization, the early universe began to look less chaotic and more coherent. Flatness explained, temperature uniformity explained. Even several exotic particle predictions that had worried physicists for years seemed to fade naturally within inflationary models. For many cosmologists, inflation became not merely plausible, but almost unavoidable. Yet hidden inside this elegant theory was another strange implication, one that would slowly grow into one of the most unsettling ideas in modern science. Because inflation was not perfectly smooth. Tiny fluctuations still existed. Minute variations in energy, almost unimaginably small, flickered through the early universe like faint ripples crossing water, and inflation stretched those ripples too. This part of the story is especially beautiful because it quietly connects the smallest scales in physics to the largest structures in existence. Quantum fluctuations, tiny trembling uncertainties normally confined to microscopic reality, were magnified by inflation until they became enormous cosmic patterns. The galaxies themselves may have emerged from ancient quantum whispers. Every star, every nebula, every planet, every ocean, every living cell, even the neurons quietly firing in your brain right now as you listen, may ultimately trace back to tiny fluctuations stretched across space-time in the universe's first fleeting moments. The thought feels almost dreamlike, that enormous galaxies were born from microscopic uncertainty, that the structure of reality began as faint ripples amplified across a rapidly expanding cosmos, and those ancient ripples still remain visible today. Scientists detect them as delicate temperature patterns spread across the cosmic microwave background, subtle unevenness scattered through ancient light like fingerprints left by the early universe itself. Without those fluctuations, the universe might have remained perfectly smooth forever. No stars, no galaxies, no gravitational gathering, no observers, just endless uniform fog expanding quietly through darkness. In a strange way, imperfection made structure possible. Tiny unevenness allowed gravity to slowly gather matter into larger forms over billions of years. Regions slightly denser than average attracted more material. Clouds formed, stars ignited, galaxies assembled themselves like drifting cities of light, and eventually, after unimaginable spans of time, conscious beings appeared inside one small corner of that process, beings capable of looking backward toward the beginning and asking how any of this happened at all. But even as inflation solved mystery after mystery, another realization slowly emerged from the mathematics. If space could expand this violently once, perhaps it could happen elsewhere too. Perhaps inflation was not a single event. Perhaps it was part of something much larger. And if that were true, then the observable universe surrounding us tonight may not be the whole cosmos at all, but only one small region where inflation briefly came to rest. As the image of the early universe continues to widen in the imagination, inflation begins to feel almost miraculous. It explains why space appears so flat, why distant regions share similar temperatures, why galaxies formed from tiny fluctuations stretched across the young cosmos. For a while, it can seem as though inflation solved everything. But cosmology has a quiet habit of doing this. A theory arrives to answer one mystery, and in doing so, opens the door to something even stranger. Because the more carefully physicists examined inflation, the more they realized that its consequences were enormous, perhaps far larger than anyone first expected. Inflation did not simply shape the observable universe. It may have hidden most of reality forever, to understand why. It helps to imagine the universe before inflation began, not the visible universe we know today, filled with galaxies and ancient light, but a much smaller connected region where everything existed close enough together to interact. Signals could travel, energy could mix, temperatures could settle into balance. Reality, though unimaginably dense and hot, still belonged to a shared conversation. Then inflation arrived, and space expanded so violently that enormous regions were pulled beyond one another's reach almost instantly. Not separated by ordinary distance alone, but by expanding space-time itself. This distinction matters deeply. If two ships drift apart slowly across calm water, one could eventually travel back toward the other. Distance alone does not prevent reunion, but inflation was different. The ocean itself expanded between the ships faster than they could cross it. Space kept creating more space, and once that process crossed a certain threshold, some regions became permanently causally disconnected. That phrase sounds technical at first, but its meaning is strangely intimate. Causality is simply the possibility of influence, the ability for one event to affect another. A conversation, a signal, a ray of light crossing darkness. To become causally disconnected means that two regions of reality can no longer exchange information at all, not because something blocks them, not because of a wall, but because space-time itself stretches too quickly for communication to survive. This changes the emotional meaning of the observable universe completely. The observable universe is not a giant container holding everything that exists. It is more like a local clearing in an infinitely expanding fog, a temporary region where light has had enough time to arrive, and every observer in the cosmos lives inside their own version of that clearing. If intelligent beings exist somewhere unimaginably distant tonight, they would also see themselves surrounded by an observable universe. Their skies would contain galaxies and ancient radiation and horizons of visibility. And from their perspective, they too might appear to sit at the center of everything. But their visible cosmos could overlap only partially with ours. Beyond a certain distance, our realities would no longer intersect at all. Their stars would remain forever unseen by us. Our Milky Way would remain forever unseen by them. Entire cosmic histories unfolding in parallel silence. This is one of the strangest emotional consequences of modern cosmology. The universe may contain vastly more existence than any observer can ever experience, and inflation may be the reason why. The realization becomes even more unsettling when physicists attempt to estimate how large the full universe might actually be. The observable universe spans an extraordinary distance already. Light reaching us from the farthest visible regions has travelled for billions upon billions of years. And because space expanded while that light travelled, those distant regions are now far farther away than intuition first suggests. Yet even that enormous visible sphere may represent only a tiny local patch. Some conservative estimates suggest the full universe could be hundreds of times larger than the observable region in every direction. Others allow for the possibility that the universe extends infinitely, an endless structure containing unimaginable numbers of galaxies beyond the horizon, perhaps infinitely many stars, infinitely many planets, possibly even infinitely many regions resembling our own. And if inflation continues in some distant regions even now, the situation becomes stranger still, because inflation may not have ended everywhere simultaneously. In our local region, inflation appears to have slowed long ago, allowing matter and galaxies to form. But elsewhere, spacetime may still be expanding at extraordinary rates. Some cosmologists describe this process almost like boiling water. Small pockets stop inflating and settle into calmer states, forming local universes like bubbles inside a much larger expanding structure. Meanwhile, the surrounding inflationary space continues growing endlessly. If this picture is correct, then our observable universe may be only one calm island inside a much larger cosmic sea, a sea still swelling beyond sight. The implications are difficult to emotionally absorb because human intuition evolved for forests, rivers, storms and mountains, not for realities larger than visibility itself. We naturally imagine that if something exists, it should eventually become reachable. But cosmology quietly suggests otherwise. Some parts of existence may be permanently inaccessible, not because we are weak, but because the architecture of space-time itself prevents contact. There is something strangely melancholy about that idea. Entire galaxies may exist forever beyond our horizon. Stars may rise and die in regions whose light will never reach Earth. Civilizations may appear and disappear in distant cosmic neighborhoods, completely disconnected from our own. Reality may contain histories forever isolated from one another, like drifting islands separated by endlessly widening oceans. And yet, there is also something beautiful hidden inside this realization, because the same inflation that created these boundaries also created the conditions for structure itself. Without inflation, the universe may never have become smooth enough for galaxies to form. Tiny fluctuations may never have expanded into stars and planets. The cosmos might have remained chaotic or collapsed too quickly for complexity to emerge. In a strange symmetry, our existence and our ignorance appear to come from the same ancient event. Inflation gave the universe order. Inflation gave the universe structure. And inflation may also have hidden most of reality forever behind unreachable horizons. The universe did not merely become large. It became fragmented into regions of visibility, small illuminated windows separated by vast stretches of expanding space-time. And from inside one such window, humanity slowly began trying to understand the shape of the larger darkness surrounding it. Perhaps that is why cosmology feels so emotionally different from other sciences. When you study a forest, you can eventually walk deeper into it. When you study an ocean, you can eventually sail farther outward. But when you study the universe itself, you eventually encounter boundaries that cannot be crossed. Not technological boundaries, not temporary ones. Fundamental limits written into the behaviour of light, time, and space itself. And somewhere beyond those horizons tonight, the rest of reality may still be unfolding in silence. As the idea of hidden cosmic regions begins to settle softly into the mind, another realization slowly follows behind it. If every observer sees only a local patch of reality, then where exactly is the centre of the universe? It is one of the oldest and most human questions imaginable. For most of history, people naturally assumed they stood near the centre of existence. Ancient civilizations looked upward and saw the heavens turning overhead each night, while the earth beneath their feet seemed still and unmoving. It felt reasonable to imagine the cosmos arranged around human life like a great celestial theatre. Over time, science slowly dismantled that comforting picture. The Earth was not the centre of the solar system. The solar system was not the centre of the Milky Way. The Milky Way itself was only one galaxy among many. And now, modern cosmology suggests something even stranger. The universe may not possess a central location at all. At least, not in the ordinary sense the human mind expects. This becomes easier to understand if you stop imagining the universe as an explosion travelling outward through empty space. That image quietly creates the illusion that somewhere far away there must still be a central point where everything began. But inflation and cosmic expansion do not behave that way. The universe is not expanding into external emptiness like smoke spreading across a room. Space itself is expanding everywhere at once. A gentle analogy often used by cosmologists involves dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No single dot sits at the centre of the expansion from the perspective of the surface itself. Each dot simply sees all the others drifting away. And importantly, the true centre of the balloon does not exist on the two-dimensional surface where the dots live. In much the same way, the universe may not contain a meaningful central point within space-time itself. Every observer instead experiences something more personal, a local visible sphere surrounding them in all directions. Imagine standing in a vast fog-covered field at night holding a lantern. The fog prevents you from seeing beyond a certain distance, so the visible world forms a glowing circle centered around you. Another traveler somewhere far away would experience the same thing. Their illuminated circle would also appear centered on themselves. Neither observer is special. The geometry of visibility creates the illusion of centrality naturally. The observable universe works in a remarkably similar way. You see distant galaxies surrounding you because light from those galaxies has had enough time to reach your location. Another civilization billions of light years away would see a different arrangement of galaxies centered around themselves. In a sense, every observer occupies the center of their own observable universe, and yet no observer occupies the center of the entire cosmos. This idea feels slippery at first because human intuition prefers fixed reference points. We want maps with middle regions and outer edges. We want clear coordinates that separate here from there. But space-time does not always obey those expectations. The deeper cosmologists looked into expansion, the more they realized that the universe behaves less like an object sitting inside space, and more like space itself changing over time. Galaxies are not simply racing through emptiness like bullets across darkness. The distances between galaxies grow because the underlying geometry of space-time stretches. You can picture raisins inside rising bread dough. As the dough expands in the oven, every raisin sees the others drifting farther away. No raisin occupies a privileged location. Expansion occurs throughout the dough itself. And because more distant raisins have more expanding dough between them, they appear to separate faster. This beautifully matches what astronomers observe in reality. The farther away galaxies are from us, the faster they appear to recede. Not because Earth occupies a special position, but because expansion affects all large-scale distances simultaneously. For some listeners, this realization can feel oddly unsettling at first. Human beings instinctively search for stable centers, a hometown, a family table, a familiar room, a place where orientation feels secure. But cosmology quietly removes the idea of a universal center altogether. The cosmos appears astonishingly democratic in this sense. Every observer sees themselves surrounded by horizons. Every observer experiences a local sphere of visibility. Every observer inhabits a temporary window into a much larger reality. And this has profound consequences. Because if observable universes overlap only partially, then there are regions of existence forever inaccessible from our location, even though they may be visible somewhere else. This means the universe does not possess one single shared view of itself. Reality is fragmented into perspectives. One civilization may observe galaxies that humanity will never see. Another may exist so far away that even the ancient glow of the cosmic microwave background looks different in their sky. Entire cosmic maps vary depending on where the observer stands, and inflation amplified this fragmentation enormously. By stretching space-time faster than light could reconnect distant regions, inflation effectively divided the larger cosmos into countless local horizons. Each observer inherits only a small visible portion of the greater structure, like windows scattered across an enormous dark cathedral. Each window reveals something real, but none reveal the whole building. There is something deeply humbling about this. Humanity often imagines scientific progress as a process of steadily removing mystery from the universe. We build larger telescopes, detect fainter signals, travel farther into space, and certainly our understanding has grown astonishingly over the centuries. But cosmology introduces a quieter possibility. Some aspects of reality may remain hidden not because knowledge failed, but because perspective itself is limited. Even perfect instruments cannot see beyond certain horizons. Even immortal civilizations could remain trapped inside local cosmic bubbles. The universe may simply be too large and too dynamic for any observer to access in full, and perhaps that is why the observable universe feels emotionally different once you truly absorb what it means. It is not merely a region of space. It is a relationship between observer and causality, a sphere defined by which ancient signals have had enough time to arrive, nothing more and nothing less. Tonight, as you rest beneath your own ceiling and your own quiet patch of sky, it is strange to imagine that you're already sitting at the center of an observable universe 70 or 80 or 90 billion light-years across. While somewhere unimaginably distant, another observer may quietly believe the same thing about their own. Both perspectives equally real, both incomplete, both surrounded by horizons beyond which the rest of existence continues silently onward. As the idea of observer-centered universes continues drifting quietly through the imagination, the cosmos begins to feel less like a single open landscape and more like a layered structure of visibility, a place filled with boundaries that are not really boundaries, invisible shores created not by stone or metal, but by time itself. One of the strangest discoveries in modern cosmology is that the universe contains several different kinds of horizons, and each horizon answers a slightly different question. What can we see? What can we ever reach? What can still influence us? What has already slipped away forever? At first, these horizons sound technical and abstract. The terminology can feel cold if presented too quickly, but underneath the complicated language lies something surprisingly human. Every horizon is really about connection, about whether two parts of reality can still speak to one another across the expanding darkness. The first and most familiar horizon is the observable limit itself, sometimes called the particle horizon. This is the boundary surrounding everything whose light has had enough time to reach us since the early universe became transparent. Beyond that distance, light is still travelling through space but simply has not arrived yet. You can imagine standing on a beach at dawn while thick ocean fog slowly begins to lift. At first, only nearby waves are visible. Then distant shapes gradually emerge farther outward as light spreads across the water. The observable universe behaves in a somewhat similar way. The longer cosmic time passes, the farther light can travel, and the larger our visible region becomes. In that sense, the observable universe is still growing. More ancient light reaches us every year. More distant regions slowly drift into visibility. But this creates a strange tension, because another horizon behaves very differently. This second boundary is called the cosmic event horizon, and unlike the observable horizon, this one marks regions from which signals sent today may never reach us in the future. That distinction is subtle, but deeply important. There are galaxies whose ancient light we can still observe tonight, because it began travelling toward Earth billions of years ago, when those galaxies were much closer. But due to the accelerating expansion of space caused by dark energy, some of those same galaxies have now become so distant that any new light they emit today will never arrive here at all. We are seeing their past, but losing contact with their future. It is difficult not to find something emotional in that realization. Entire galaxies slowly fading into permanent silence, not vanishing physically, but slipping beyond communication, like hearing echoes from someone already walking out of reach through an endlessly lengthening corridor. And this process is still happening now. The universe is not merely expanding, its expansion is accelerating. Space itself keeps creating more distance between large cosmic structures over time. Eventually, many galaxies will recede so rapidly that they disappear beyond the event horizon forever. Future observers may look into a much emptier sky than ours, but before reaching that melancholy future, there is another horizon worth understanding first. This one is often called the Hubble sphere. The name sounds intimidating at first, though the idea underneath is surprisingly intuitive. The Hubble sphere marks the distance where cosmic expansion causes galaxies to recede from us at the speed of light. Closer than this boundary, galaxies drift away more slowly. Farther than this boundary, expansion carries them away faster than light itself. That statement sometimes startles people because they remember being told that nothing can move faster than light. But relativity places that limit on motion through space. The universe does something stranger. Space itself expands. A useful image is to imagine small coins resting on an enormous rubber sheet. If the sheet stretches gently, nearby coins drift apart slowly. But coins separated by huge distances move apart much faster because far more stretching occurs between them. Neither coin is breaking the rules of physics locally. The distance grows because the sheet itself changes. The Hubble sphere represents the region where that stretching becomes extreme enough that recession reaches light speed, and yet, strangely, galaxies beyond the Hubble sphere can still remain visible. This often confuses people the first time they encounter it. The reason is subtle. Light emitted long ago may still continue travelling toward us, even while the space between us expands. Some photons slowly make progress through an expanding cosmic river, especially if conditions change over time. So the Hubble sphere is not a hard wall, It is more like a shifting current within the larger geometry of space-time, and beyond all these horizons lies perhaps the quietest and most haunting boundary of all, the future visibility limit. This horizon asks not what we can see now, but what we will ever be able to see, even in principle. Because although the observable universe grows in some ways, dark energy simultaneously cuts off more and more regions permanently. Some distant events occurring right now will never become visible to humanity, no matter how long civilization survives. Their light will never arrive, their histories will never intersect with ours. The universe contains futures we will never witness. There is something profoundly humbling about this layered architecture of horizons. The cosmos is not simply large, it is selectively accessible. Different regions belong to different levels of causal relationship. Some can still influence us, some only reveal their ancient past. Some are forever unreachable already, and some may never enter our observable universe at all. These boundaries are not artificial limitations imposed by human weakness. Even a perfect civilization with perfect instruments would still confront them, because the limits emerge from the structure of space-time itself. The same laws that allow stars to shine and galaxies to form also create regions forever beyond communication. In a strange way, the universe resembles a vast mansion filled with softly closing doors. For a time, distant rooms remain visible through long hallways. Then the hallways stretch, the lights dim, the doors drift farther apart, and eventually, some rooms become unreachable forever. Yet tonight, inside our own temporary window of visibility, the universe still offers extraordinary things to see. Ancient radiation from the birth of atoms, galaxies whose light began travelling before Earth existed, patterns stretched across billions of light years, all arriving together inside one fragile era of cosmic history where observation is still possible. And perhaps that is part of what makes cosmology feel so quietly precious. We are living during a brief period when the universe has not fully hidden itself yet. As the layered horizons of the universe begin to settle gently into place, another realization slowly emerges from the darkness beside them. When you look far into space, you're also looking far into the past. This is one of the strangest and most beautiful consequences of living in a universe where light takes time to travel. The moon appears not as it is now, but as it was a little more than 1 second ago. Sunlight crossing the morning sky left the sun around 8 minutes earlier. Some of the brighter stars overhead belong not to the present moment, but to years already gone by. Their light began its journey long before tonight's quiet room existed exactly as it does now. And distant galaxies push this idea into something almost dreamlike. The farther away a galaxy is, the longer its light has travelled to reach Earth. Some galaxies appear to us not as they are today, but as they were when dinosaurs still walked across our planet. Others appear as they were before Earth itself fully formed. Telescopes do not merely observe distant objects, they observe ancient time. In a sense, every night ski is a museum of delayed messages, and if you continue travelling farther outward through distance, eventually you reach a boundary unlike any other, a faint glow filling all directions of space, not starlight, not galaxy light, but ancient radiation left over from the early universe itself. Scientists call it the cosmic microwave background, and although its name sounds cold and technical, it is really something astonishingly poetic. It is the oldest light humanity can see. To understand why this ancient glow exists at all, we must travel back to a time long before stars, planets, or galaxies appeared, back when the universe was still unimaginably hot. so hot that atoms could not survive. In those early ages, space resembled a dense, glowing fog of particles and radiation constantly colliding with one another. Light could not travel freely because photons, tiny packets of light energy, scattered endlessly in every direction. The young universe was opaque, not dark, but blindingly bright, like standing inside a glowing storm cloud where every beam of light is repeatedly interrupted before travelling any meaningful distance. And then, slowly, as expansion continued, the universe cooled. Temperatures fell enough for electrons and atomic nuclei to finally join together into stable atoms. Suddenly, light no longer scattered constantly. Space became transparent for the first time, and the ancient photons released during that moment began travelling freely across the cosmos. Those photons are still travelling today. Some of them are arriving at Earth right now, after crossing the universe for nearly its entire history. That realization alone feels almost impossible to emotionally absorb. The light detected by radio telescopes tonight began its journey before galaxies fully assembled, before stars like our sun existed, before planets carried oceans or clouds or forests. It comes from a universe only a few 100,000 years old, cosmically speaking, infancy. And because this radiation surrounds us in every direction, it creates a kind of visible boundary to the observable universe, not a physical edge, not the end of existence, but the farthest epoch from which light can currently reach us. Beyond the cosmic microwave background lies an even earlier universe, but one hidden behind the glowing fog of the primordial plasma. Light from earlier times cannot travel directly to us because the young universe had not yet become transparent. In that sense, the cosmic microwave background acts almost like a veil, or perhaps like the oldest surviving photograph of reality, a faded image carried across billions of years. What makes this ancient glow even more extraordinary is its smoothness. When scientists first measured it carefully, they discovered that its temperature appeared almost identical across the sky. Whether observing north or south, left or right, the differences were astonishingly tiny. This became one of the strongest clues supporting inflation, because regions that seem impossibly distant today appear to have once existed close enough together to share energy and balance their temperatures before inflation rapidly stretched them apart. But the microwave background is not perfectly smooth, and that imperfection changed everything. Tiny fluctuations remain scattered through the ancient radiation, minute differences in temperature so subtle that they resemble faint ripples across a calm lake. At first glance, those ripples may appear insignificant, but they are among the most important structures in cosmology, because those slight, uneven regions became the seeds of galaxies. Areas just a little denser than average slowly gathered more matter through gravity. Over billions of years, those tiny fluctuations grew into stars, galaxies, clusters, and eventually the large-scale cosmic web itself. In a profound sense, every visible structure in the universe emerged from faint irregularities hidden inside this ancient light. Without them, reality might have remained smooth forever. No galaxies, no planets, no observers, only endless uniform expansion. There is something deeply moving about that. Tiny imperfections in the early universe eventually becoming forests, oceans, music, cities, memory, language, and conscious minds wondering where they came from. The cosmic microwave background also allowed scientists to measure something else extraordinary: the geometry of spacetime itself. Ancient sound waves moved through the hot plasma of the young universe before transparency emerged. These waves left subtle patterns frozen into the microwave background, patterns that acted like cosmic measuring tools spread across the sky. And when astronomers studied those patterns carefully, they discovered something astonishing. the geometry of the observable universe appeared almost perfectly flat. Again and again, the universe kept returning to the same quiet mystery. Balanced, smoothed, expanded, shaped by some ancient process of extraordinary power. The cosmic microwave background became one of the strongest pieces of evidence that inflation truly occurred, not because inflation was directly photographed, but because its fingerprints may still remain spread faintly across the oldest visible light in existence. Even now, as you rest quietly listening in the dark, that ancient radiation continues passing invisibly through your room, a faint sea of primordial photons flowing through walls, through air, through space itself. Ancient light from the childhood of the cosmos still surrounding Earth after billions of years of travel. And perhaps that is one of the most beautiful things modern cosmology has revealed. The universe remembers its beginning, not perfectly, not completely, but enough for conscious beings, born unimaginably later, to slowly piece together the story written into the oldest light of all. As the faint glow of the cosmic microwave background continues quietly surrounding us, another remarkable detail begins to emerge from within it. The early universe was not silent. Long before stars ignited, long before planets cooled, long before oceans reflected moonlight or living creatures breathed beneath clouds, the universe itself rang with waves, not sound in the ordinary sense we experience on Earth. No human ears existed then, and outer space today is far too empty for sound to travel normally. But the young universe was different. In those early ages, matter and radiation were packed together so densely that the cosmos behaved less like empty space and more like a glowing fluid, a vast ocean of hot plasma. And inside that ocean, pressure and gravity continuously pushed against one another. Gravity tried to pull matter inward, radiation pressure pushed outward. The result was a series of enormous oscillations rippling through the young universe like waves moving across water. To picture this softly, imagine dropping rain onto the surface of a still pond at night. Circular ripples spread outward from each disturbance. Now imagine those ripples not across water, but across the entire early cosmos. Regions of slightly higher density compressed under gravity. Heat and radiation pushed back. Compression became expansion. Expansion became compression again. And these oscillations travelled outward through the primordial plasma for hundreds of thousands of years. The scale involved is almost impossible to emotionally grasp. These were not waves crossing oceans or continents. They were waves stretching across regions larger than the entire galaxy clusters. Ancient vibrations moving through the young universe before stars even existed. And then something extraordinary happened. When the universe cooled enough for atoms to form and light began travelling freely, those cosmic sound waves effectively froze in place. The ripples stopped propagating. Their patterns became imprinted into matter itself, like rings suddenly trapped inside ice. The ancient oscillations left behind slightly preferred distances between galaxies, subtle statistical patterns still visible billions of years later across the large-scale structure of the universe. Modern cosmologists call these patterns baryon acoustic oscillations. But behind the intimidating terminology lies something strangely beautiful. They are fossilized echoes from the childhood of the cosmos, ancient sound waves preserved across space-time, and these frozen ripples became one of humanity's most important tools for measuring reality itself. Because the size of those primordial waves can be calculated from the physics of the early universe. They act like a kind of standard ruler spread throughout the cosmos. By observing how large these patterns appear at enormous distances, scientists can infer the geometry of space. The logic resembles something surprisingly ordinary. Imagine walking through thick fog toward a distant street lamp whose true size you already know. If the lamp appears unusually small, you infer that it must be farther away. If it appears distorted, you may learn something about the air or the landscape between you and the lamp itself. Cosmologists do something similar with ancient cosmic patterns. The frozen sound waves provide a ruler. The universe provides the geometry through which that ruler is observed, and the results have been astonishing. Again and again, observations suggest that large-scale space appears almost perfectly flat. Not because anyone travelled to the edge of the universe and measured it directly, but because ancient ripples preserved inside radiation and galaxy distributions behave exactly the way flat geometry predicts. There is something quietly elegant about this. Human beings never stepped outside the universe to inspect its shape from afar. Instead, we learn to read subtle patterns hidden inside ancient light, almost like deciphering the memory of space-time itself. And the deeper scientists looked into these primordial ripples, the more another realization emerged. The universe appears understandable through patterns, not random chaos, but structure. Tiny fluctuations amplified by inflation eventually became galaxies. Ancient plasma oscillations became large-scale cosmic maps. Invisible geometry revealed itself through faint statistical echoes. Reality began to resemble an immense interconnected tapestry, where the smallest events in the early universe still shape the larger structures billions of years later. In some ways, this is one of the most astonishing features of cosmology. The observable universe remembers its origins, not perfectly, of course. Expansion, gravity, and cosmic evolution blur many details over time, but enough traces remain for careful observers to reconstruct ancient events with extraordinary precision, like archaeologists rebuilding forgotten civilizations from broken fragments buried beneath sand. Except in cosmology, the ruins are galaxies and radiation fields spread across billions of light years, and the ruins still glow faintly in the dark. There is also something emotionally comforting about the softness of these measurements. The universe did not reveal itself through giant glowing signs or dramatic cosmic messages. Instead, understanding emerged slowly from tiny variations, slight asymmetries, delicate fluctuations hidden inside ancient light, almost whispers. It reminds us that some of the deepest truths in reality arrive quietly, not with violence, but with patience. Still, despite all these successes, the measurements introduced another unsettling implication. If the observable universe appears so smooth and flat across enormous scales, then inflation may have stretched space-time vastly farther than what we can currently observe. The visible cosmos may represent only one tiny region within a much larger geometry whose true size remains beyond measurement, and the ancient sound waves preserved in the cosmic microwave background hint at this indirectly. Because although we can map patterns inside our observable horizon, we cannot see the larger structure beyond it. We do not know whether space eventually curves differently farther away, whether it loops around itself, or whether it extends infinitely beyond all visibility. Our cosmic rulers measure only the illuminated patch we inhabit. Beyond the horizon, the geometry of reality may continue in ways forever inaccessible. There is something strangely poetic about that limitation. Humanity learned to read the echoes of the early universe. We learned to detect ripples frozen into ancient radiation. We learned to infer the shape of space-time itself from patterns billions of years old. And yet even these extraordinary tools still leave us standing inside a local window of visibility, surrounded by horizons beyond which the rest of existence remains silent. Perhaps that is part of what makes cosmology feel so dreamlike late at night. The more precisely we measure reality, the larger and more mysterious it becomes. As the ancient ripples of the early universe slowly fade into the background of thought, another question naturally begins to rise beside them. If the observable universe is only the region we can currently see, then how large is the rest? It is one of those questions that sounds simple for a few seconds before the mind suddenly realizes what it is actually asking. Not the size of galaxies, not the size of clusters, not even the size of the observable universe itself, but the size of everything beyond it. And the honest answer from modern cosmology is both humbling and strangely beautiful. We do not know. Yet even within that uncertainty, physics still offers clues. The observable universe already stretches across distances so enormous that language struggles to hold them comfortably. Light from the farthest visible regions has travelled for nearly the entire history of the cosmos before finally reaching Earth. And because space expanded during that journey, those distant regions are now vastly farther away than simple intuition suggests. If you could somehow freeze cosmic expansion and travel instantly from one side of the observable universe to the other, the journey would cross unimaginable oceans of galaxies, trillions upon trillions of stars, dark voids stretching between galaxy clusters like silent cosmic deserts. And yet, according to many cosmological models, this enormous visible sphere may still represent only a tiny local patch of a much larger structure. Some measurements suggest that if the full universe is finite, its radius must still be at least hundreds of times larger than the observable region. That alone is difficult to emotionally process. Imagine standing on a beach and discovering that the visible ocean before you, already so enormous it seems endless, is actually only a small inlet connected to waters vastly larger beyond the horizon. Now enlarge that feeling to cosmic scale. The observable universe may contain roughly 2 trillion galaxies, and beyond the horizon there may exist millions of other observable universe-sized regions, each filled with their own galaxies, stars and histories forever unreachable from Earth. The mind instinctively tries to convert these numbers into images, but eventually imagination begins to blur. Scale itself starts losing meaning. And this is where cosmology becomes emotionally unusual. Most sciences eventually lead toward precision and familiarity. You study something long enough and it becomes easier to mentally grasp, but cosmology often does the opposite. The deeper humanity looked into the universe, the larger reality became. In some models, space may even extend infinitely, not merely very large, not unimaginably huge, but literally without end. An infinite cosmic structure where galaxies continue beyond every horizon forever. The human brain does not handle infinity naturally. Our thoughts evolved around forests, rivers, seasons, and finite landscapes. Infinity feels less like a number and more like standing at the edge of conceptual fog where ordinary imagination begins dissolving. And yet many cosmologists quietly accept the possibility because inflation naturally tends to produce universes far larger than observable regions. Once inflation begins stretching space-time rapidly, even a tiny initial patch can grow beyond comprehension. Our visible universe may simply be one calm local region within an enormously larger geometry extending far beyond all possible observation. There is something strangely intimate about this realization. Tonight, every memory you possess, every city on Earth, every ocean and mountain and sleeping animal, every human story, every work of art, every civilization that ever existed, all of it fits inside one observable patch of a much larger reality. Human history itself becomes almost microscopic against the scale involved. And yet, strangely, this does not necessarily make existence feel meaningless. If anything, it can create the opposite sensation, a kind of quiet tenderness. because conscious life appears inside one temporary illuminated region of an immense hidden cosmos, and still manages to ask questions about the whole, still manages to wonder, still manages to look outward. There is also another subtle implication hidden inside these enormous scales. If the universe truly extends vastly beyond the observable horizon, then somewhere beyond visibility there may exist regions remarkably similar to our own. After all, the laws of physics we observe appear fairly uniform throughout visible space. Galaxies form according to familiar gravitational processes. Stars ignite through recognizable nuclear reactions. Chemistry follows stable patterns across the cosmos. If those same physical rules continue indefinitely, then sufficiently large space may eventually repeat arrangements of matter. Some physicists have pointed out that in an infinite universe, combinations of particles would eventually recur somewhere far enough away, not because of destiny, not because of mysticism, but because finite arrangements repeated across infinite space inevitably reappear. The idea sounds almost unsettlingly philosophical. Somewhere unimaginably distant, another Earth-like planet may orbit another star. Another civilization may wander about cosmic horizons beneath another night sky. Perhaps not identical, perhaps profoundly different, but still shaped by the same deep physical structure. Of course, these ideas remain speculative at enormous scales. The truth is that horizons permanently limit certainty. We can infer possibilities mathematically, but direct observation eventually fails. And this is one of the central emotional tensions in cosmology. The universe appears understandable enough to reveal its vastness, but perhaps too large to ever reveal itself completely. Even our most advanced telescopes cannot see beyond the observable horizon, because the limitation is not technological, it is causal. Light itself has finite travel time. Expansion itself creates separation. The universe withholds information not intentionally, but structurally. There is something oddly peaceful in accepting that. Not every mystery exists to be solved completely. Some realities may always remain partially hidden beyond the reach of observation, and perhaps that hiddenness gives the cosmos part of its emotional depth. After all, imagine if every horizon vanished instantly. If the entire universe could suddenly be seen at once with perfect clarity. No distance, no mystery, no invisible regions beyond the fog. In some strange way, the universe might feel smaller, less dreamlike, less alive with possibility. But instead, reality stretches outward beyond sight, beyond causality, beyond certainty itself. An endless dark ocean illuminated only locally by ancient light. And inside one small visible region of that ocean, humanity quietly continues trying to understand the shape of the unseen waters surrounding it. As the unimaginable scale of the universe continues expanding softly in the mind, another question slowly emerges from the darkness beyond the horizon. If the universe extends far beyond what we can observe, what shape does the whole thing actually have? At first, the question sounds almost impossible to approach, not because it lacks meaning, but because human intuition was never designed for it. We evolved walking across forests and coastlines beneath a sky that appeared flat and endless. Everyday experience quietly teaches the brain that space behaves in simple ways. You move forward, you eventually reach boundaries. Rooms have walls, roads have endings, but the universe may not follow those expectations at all. And strangely, one of the most fascinating possibilities in cosmology is that space itself could be finite, without possessing an edge anywhere. This sounds contradictory when first encountered. How can something be finite but endless at the same time? The easiest way to soften the idea into something intuitive is to begin not with the universe, but with Earth. Long ago, many people imagined the Earth as flat because the local ground appears flat from ordinary human perspective. But eventually, sailors and travellers realised something curious. You could continue moving in one direction for long enough, and eventually arrive back where you started without ever encountering a physical edge. The surface was finite. You could measure its size, and yet no cliff marked the end of the world. Space itself may behave similarly on unimaginably larger scales. A being living inside such a universe might travel endlessly, without ever reaching a boundary because the geometry quietly curves back into itself. Not unlike walking forever across the surface of a globe. This distinction introduces an important idea in cosmology: the difference between geometry and topology. Geometry describes local shape, whether space appears flat or curved nearby. Topology describes the deeper connected structure underneath. A sheet of paper and a cylinder may both appear locally flat to a tiny ant crawling across them, but globally, their structures differ enormously. One stretches openly outward, the other loops around. In the same way, the observable universe may appear nearly flat while the larger topology of space-time remains far stranger beyond our horizon. One particularly famous example is something called a toroidal universe. The terminology sounds intimidating at first, but the intuition underneath is surprisingly playful. Imagine an old video game like Pac-Man. When the small character exits one side of the screen, he reappears instantly on the opposite side. The world loops. There is no final wall, no outer edge. Movement simply reconnects space back into itself. Some cosmological models suggest reality could behave in a somewhat similar way on enormous scales. Travel far enough in one direction, and in principle, you might eventually return to your starting point from the opposite side. The universe would remain finite, but unbounded. There is something deeply dreamlike about this possibility, a cosmos where every direction quietly folds back into itself, where distance becomes circular rather than terminal, where journeys continue not toward endings, but toward returns, and topology becomes even stranger when imagined emotionally rather than mathematically. Picture wandering through an endless hallway lined with identical doors and dim golden lamps. The corridor appears infinite at first, but after countless hours of walking, subtle details begin repeating. A familiar painting appears again, a crack in the wall returns. The hallway was never truly infinite. Its structure simply looped too broadly for immediate recognition. Or imagine standing inside a mirrored room so enormous that reflections gradually fade into darkness. The space feels boundless, yet hidden symmetries quietly connect distant regions together. These images are imperfect, of course. Real cosmological topology operates in dimensions and scales far beyond ordinary architecture, but they help soften the emotional intuition. The universe may not end because ending itself may be the wrong concept. And remarkably, modern cosmology does not entirely rule this out. When scientists measure the large-scale geometry of the observable universe, space appears astonishingly flat. But local flatness alone cannot determine the global topology of reality. Earth again provides the intuition. From ground level, Earth feels flat beneath your feet, even though the larger planet curves into a sphere. A tiny local region reveals very little about the whole structure. Similarly, our observable patch of space-time may simply be too small relative to the larger cosmos for global curvature or looping patterns to become obvious. Inflation complicates this even further. If the early universe expanded enormously during inflation, then any larger loops or curvature could have been stretched so vastly that they now extend far beyond our observable horizon. the observable universe might resemble a tiny magnified patch of a much larger structure, whose full topology remains invisible to us. Like standing so close to an enormous sculpture that only a tiny smooth fragment can be seen at once. This creates a fascinating emotional tension in cosmology. The universe may possess a hidden large-scale structure, but inflation may have permanently concealed it from direct observation. Reality could contain loops, symmetries, or connected geometries extending beyond all visible horizons, while every observer remains trapped inside local regions too small to perceive the whole. And yet scientists still search for clues. Because if space truly wraps around itself, light travelling across the universe might occasionally produce repeating patterns in the sky. Ancient radiation could potentially arrive along multiple paths. Distant structures might appear duplicated in subtle ways. Cosmologists have spent years looking for such signatures hidden inside the cosmic microwave background. So far, no definitive evidence has emerged, but importantly, absence of evidence is not evidence of absence. The universe may simply be too large, too inflated, too vast for its deeper topology to reveal itself within our visible patch. There is something strangely beautiful about that uncertainty. The cosmos may possess a hidden shape beyond perception, not because nature wishes to deceive us, but because space-time itself stretches farther than visibility can reach. Tonight, as you rest quietly beneath your own small corner of the sky, it is worth lingering for a moment inside that thought. The universe may not have an edge waiting somewhere beyond the galaxies. No final wall, no ending cliff, no place where existence suddenly stops. Instead, reality may curve softly back into itself, like a path through darkness that eventually returns home without ever encountering an end at all. As the possibility of a looping universe slowly settles into the imagination, another question naturally follows beside it. If space truly folds back into itself in some hidden way, could we ever know? At first, the answer might seem impossible. After all, humanity cannot step outside the universe to inspect its shape from afar. We are embedded inside space-time itself, observing from one small local region surrounded by cosmic horizons. And yet cosmologists have found remarkably creative ways to search for clues, not by travelling to the edge of the universe, but by carefully examining ancient light. Once again, the cosmic microwave background becomes our guide. That faint radiation filling all directions of space does more than reveal the early universe. It also acts almost like a giant screen stretched across the sky, a surface carrying subtle information about the geometry and history of space-time itself. If the universe possesses a non-trivial topology, if space quietly loops or reconnects beyond visibility, then certain patterns might repeat within this ancient radiation. Light travelling through a looping universe could potentially arrive along multiple paths. In principle, observers might detect matching circular patterns in different regions of the cosmic microwave background. Imagine standing inside an enormous hall lined entirely with mirrors. A single candle flame may appear many times from different directions, because light repeatedly reflects across the room. The images would not be separate candles, but repeated views of the same source. Some cosmologists suspect the universe could produce faintly similar effects on unimaginable scales, not through mirrors, but through topology itself. If space reconnects, ancient radiation may wrap around the cosmos in subtle ways before reaching us. Different regions of the sky could contain matching temperature variations, delicate circular fingerprints hinting that distant areas are secretly connected. This idea became one of the most fascinating searches in observational cosmology. Scientists carefully analysed maps of the microwave background looking for these possible repetitions. Sensitive satellites measured tiny temperature fluctuations spread across the sky with astonishing precision. Researchers searched for mirrored circles, repeated patterns, hidden symmetries. So far, however, the evidence remains uncertain. No unmistakable repeating structure has been found. And yet that absence does not close the question, because inflation complicates everything once again. If the universe experienced enormous inflationary expansion in its earliest moments, then any looping structure may have been stretched vastly larger than the observable horizon itself. The repeating patterns could exist, but at scales far beyond what humanity can currently observe, like standing inside an immense cathedral while carrying only a small flashlight. The local walls may appear smooth and ordinary, while the greater architecture remains hidden in darkness beyond the beam. This is one of the recurring themes quietly emerging throughout cosmology. Again and again, physics hints that reality may possess structures larger than visibility itself, not merely unknown, but potentially unobservable. There is something emotionally peculiar about searching for patterns that may almost exist inside perception. Patterns not fully visible, but nearly. Cosmology sometimes feels less like solving a puzzle and more like hearing faint music through a distant wall. You recognize fragments of melody. You sense underlying order, but complete certainty remains elusive. And perhaps nowhere is this feeling stronger than in the strange anomalies scattered through the cosmic microwave background itself. Most of the microwave background behaves exactly as modern cosmology predicts. Its temperature fluctuations match inflationary models with extraordinary accuracy. The large-scale structure of galaxies agrees remarkably well with the patterns seeded in the early universe. But a few features remain quietly unusual, not dramatic enough to overturn cosmology, not clear enough to ignore entirely. One of the most famous is known as the cold spot. In one region of the microwave background, temperatures appear slightly lower than expected across an unusually large area of sky. Some researchers suspect this may simply reflect statistical chance, an ordinary fluctuation appearing temporarily meaningful because humans naturally search for patterns. Others wonder whether enormous cosmic voids between galaxies could partially explain the effect, and a few speculate more cautiously about deeper possibilities involving structures beyond the observable horizon. No consensus exists, and importantly, most cosmologists remain careful not to overinterpret the anomaly. Yet the cold spot still carries a strange emotional power, because it feels like a faint irregularity in the universe's otherwise smooth memory. Another curious feature carries an even stranger nickname, the axis of evil. Despite sounding almost mythical, the term originally emerged somewhat jokingly among physicists studying unusual alignments in large-scale microwave background patterns. Certain fluctuations appeared more organized along particular directions than simple models initially expected. Again, the evidence remains debated. Some scientists suspect subtle measurement effects. Others believe the alignments may simply arise by chance within complex datasets. But the anomalies remain intriguing enough that discussions continue. And then there are the quasar-dipole observations, hints that certain distant structures may exhibit large-scale directional asymmetries difficult to fully explain within standard expectations. None of these observations prove exotic cosmology. None confirm hidden universes or giant topological loops, and maintaining that scientific caution matters deeply. Because the history of cosmology contains many apparent mysteries that later dissolved under improved observations and better data. At the same time, science advances precisely because careful observers remain willing to notice small inconsistencies, not sensationally, not dramatically, but patiently, quietly. The universe rarely shouts its deepest truths. More often, it whispers through tiny deviations and faint patterns hidden inside enormous datasets. And this creates a beautiful tension within modern cosmology. The observable universe appears astonishingly orderly, yet not perfectly understood. Most structures line elegantly with inflationary theory and general relativity. The cosmos behaves with extraordinary consistency across vast scales. And yet here and there, small irregularities linger at the edge of explanation, like faint fingerprints on glass, almost visible under certain light, never fully disappearing. Tonight, perhaps the most peaceful response is neither certainty nor disbelief, only openness, the willingness to recognize that the universe may contain structures larger and stranger than our current perspective allows, while also accepting that not every anomaly becomes a revolution. Reality is subtle, and cosmology teaches patience better than almost any other science, because the sky does not reveal itself quickly. Its answers arrive across billions of years of light travel, hidden inside ancient radiation, scattered through distant galaxies, waiting for quiet minds willing to notice patterns resting softly at the edge of visibility. As the faint irregularities hidden inside ancient light slowly fade into the background of thought, another possibility begins quietly unfolding from inflation itself, a possibility so large that it changes the emotional scale of cosmology entirely. Until now, inflation has mostly appeared as a moment in the distant past, a violent expansion that flattened space, smoothed the young universe, and stretched tiny quantum fluctuations into galaxies, something that happened and then ended. But over time, physicists began asking a difficult question. What if inflation did not stop everywhere at once? At first, the idea sounded almost accidental. During inflation, spacetime expanded extraordinarily rapidly because of an underlying energy state filling the early universe. In some regions, that energy may have decayed quickly, allowing ordinary cosmic evolution to begin. Matter formed, radiation cooled, galaxies eventually emerged. But quantum physics introduces uncertainty into nearly everything. Tiny fluctuations ripple constantly through reality at microscopic scales. Usually those fluctuations are unimaginably small and short-lived. Yet inflation amplifies tiny effects enormously, and under certain models this means inflation may end unevenly. Some regions stop inflating, others continue expanding, and, because inflating space grows so rapidly, the total inflating volume can keep increasing forever, even while local pockets settle into calmer states. This idea became known as eternal inflation. The phrase sounds dramatic at first, but its underlying logic grows surprisingly naturally from the same inflationary physics already used to explain the observable universe. To soften the intuition, imagine a vast pot of gently boiling water. Inside the water, bubbles continuously form. Each bubble represents a local region where conditions changed and a new environment emerged. But the surrounding water continues boiling, generating more bubbles endlessly. In eternal inflation, our observable universe may resemble one such bubble, a local calm region where inflation ended long ago. Meanwhile, beyond our horizon, inflation may still continue elsewhere across enormously larger scales, not everywhere, not uniformly, but endlessly in total. Another image sometimes helps. Picture an infinite dark ocean beneath a quiet night sky. Across the surface, islands slowly emerge from the water. Each island develops its own landscapes, weather patterns, rivers, mountains, and histories. Travelers living on one island may never reach the others because the ocean between them expands too quickly. Each island becomes its own local world. Inflationary cosmology suggests reality itself may behave in something like this way. Our observable universe would then become not the whole cosmos, but one region among many, a local event inside a much larger inflating structure. This realization changes the emotional meaning of the Big Bang itself. For much of the 20th century, people commonly imagine the Big Bang as the beginning of everything, a singular starting point from which all space and time emerged simultaneously. But eternal inflation softens that picture. In many models, the hot Big Bang that produced our observable universe may not have been the absolute beginning. Instead, it may represent the moment inflation ended locally within our region, releasing energy into matter and radiation, and beginning the familiar cosmic evolution we now observe. Elsewhere, inflation may continue still. Other regions may experience their own Big Bang-like transitions independently. Reality becomes less like one single explosion, and more like a constantly growing cosmic landscape filled with isolated pockets of structure. There is something profoundly disorienting about this idea at first. Human intuition naturally seeks singular origins, one universe, one beginning, one cosmic story. But eternal inflation suggests the larger cosmos may behave more like weather than architecture. Local conditions form and evolve within an endlessly expanding background whose full extent may never be knowable. And importantly, this picture did not emerge because physicists wanted a philosophical multiverse. It emerged because certain inflationary equations appeared difficult to stop completely. Inflation, once started, often tends to continue somewhere, almost stubbornly. The mathematics repeatedly pushed cosmologists towards scenarios where new regions of space-time keep inflating indefinitely, while localized pockets settle into ordinary universes. This is why many physicists discuss eternal inflation cautiously but seriously, not as fantasy, but as a possible consequence of already successful cosmological ideas. Still, enormous uncertainty remains. Direct evidence for eternal inflation is extremely difficult, perhaps impossible, to obtain. Other inflating regions may forever remain beyond our causal horizon. Their light can never reach us because space-time expands too rapidly between regions. In this sense, eternal inflation returns us once again to one of the deepest themes running quietly through cosmology. Reality may be vastly larger than observation. The universe keeps hinting that visible structure represents only a local fragment of something greater, and every time humanity extends its understanding outward, the hidden region grows larger too. There is also something strangely emotional about imagining isolated cosmic bubbles drifting beyond one another's horizons forever. Inside one region, stars form and civilizations emerge. Inside another, entirely different histories unfold. Elsewhere, conditions may never allow galaxies to form at all. Some universes may collapse rapidly, others may expand almost empty, and countless others may remain forever dark and unreachable. The observable universe becomes less like the entire cosmos, and more like one room illuminated briefly within an enormous unseen structure. Yet despite the scale and abstraction of these ideas, something deeply human remains at the center of them. Because eternal inflation is ultimately an attempt to answer questions that emerged from simple observations. Why is space so flat? Why is the cosmic microwave background so uniform? Why do galaxies exist at all? Theories grew larger because the questions themselves demanded deeper explanations, and perhaps that is one of the quiet lessons cosmology keeps offering. The universe is under no obligation to remain emotionally comfortable for the human mind. Sometimes the simplest observations lead toward realities far stranger than intuition ever expected. A smooth sky, a flat cosmos, tiny fluctuations in ancient light, and from those subtle clues, an entire landscape of possible universes slowly begins unfolding beyond the observable horizon. As the image of countless inflationary regions slowly drifts outward through the imagination, another question naturally follows behind it. If different cosmic bubbles can form independently, might they also behave differently? It is one of the strangest implications hidden inside certain multiverse ideas. Not merely many universes, but many possible versions of physical reality itself. To understand why physicists even consider this possibility, it helps to remember something easy to overlook in everyday life. The universe depends on balance. Stars shine because the fundamental forces of nature possess remarkably specific strengths. Atoms remain stable because electric attraction and quantum behavior cooperate within narrow ranges. Chemistry unfolds through precise interactions between particles. Even the long lifetimes of stars depend delicately on how nuclear reactions proceed deep inside stellar cores. Small changes to these underlying relationships could dramatically reshape reality. If gravity were significantly stronger, stars might burn through their fuel too quickly and collapse rapidly. If it were weaker, matter might struggle to gather into galaxies at all. If electromagnetic interactions changed too much, atoms themselves could become unstable. Chemistry, and perhaps life as we know it, might never emerge. The universe appears strangely well suited for complexity, and this realization led physicists toward a fascinating possibility. Perhaps our observable universe is only one realization among many possible physical arrangements. In some models, inspired partly by string theory and inflationary cosmology, the deeper structure of reality may allow enormous numbers of different stable configurations. Each region settling out of inflation could potentially inherit slightly different physical conditions, different balances of forces, different particle properties, different cosmic outcomes. The mathematics behind these ideas can become extremely dense very quickly, filled with extra dimensions, quantum fields, and exotic geometries, but emotionally, the intuition underneath is surprisingly simple. Imagine baking bread using slightly different recipes each time. One loaf rises beautifully, another becomes dense and heavy, another collapses entirely. The ingredients remain related, but small differences produce very different worlds. Some physicists suspect reality itself may operate similarly on cosmic scales. Our universe may simply be one region where the conditions happen to permit long-lived stars, complex chemistry, planets, and eventually conscious observers. Elsewhere, the outcomes could differ enormously. Some universes may expand too quickly for galaxies to form. Others may collapse before stars fully ignite. Some may contain only short-lived particles drifting through darkness. Others may glow with stars vastly different from anything in our sky. There could even be regions where chemistry itself behaves in unfamiliar ways, making ordinary matter impossible. This is where the emotional atmosphere of cosmology begins shifting into something almost dreamlike. Reality stops feeling singular. The laws of physics themselves begin appearing local rather than absolute. And yet, despite how surreal these ideas sound, many physicists approach them cautiously rather than dramatically, because the multiverse is not being proposed casually as fantasy. It emerges from attempts to explain why our universe possesses the specific properties it does, why these constants, why these balances, why this structure capable of supporting complexity. One possible answer is selection. In a vast enough cosmic landscape containing many physical outcomes, conscious observers naturally arise only in regions where stable complexity becomes possible. This idea is sometimes called the anthropic principle, though the phrase often sounds far more mystical than intended. At its core, the logic's fairly modest. Observers can only appear in universes where observation is physically possible. Fish naturally find themselves in water rather than deserts. Human beings naturally find themselves inside a universe compatible with chemistry, stars, and long-term stability. Still, there is something emotionally strange about realizing how delicately balanced reality may be. The stars above your head tonight depend on precise physical relationships established billions of years ago. The carbon in your body formed because certain nuclear processes inside ancient stars unfolded at exactly the right rates. The chemistry allowing memory and consciousness emerge from a universe balanced carefully enough for complexity to persist. Tiny changes might erase all of it. No forests, no oceans, no voices speaking softly in darkened rooms, no civilizations asking questions about the cosmos. Only different forms of reality unfolding elsewhere under unfamiliar laws. And yet perhaps the most unsettling part is not that other universes might differ from ours, it is that we may never directly observe them. The same inflationary expansion that could generate separate cosmic regions also isolates them behind causal boundaries. Light cannot cross between inflating bubbles once spacetime expands sufficiently rapidly. Entire universes may exist forever disconnected from one another, not hidden by technology, hidden by causality itself. Again and again, cosmology returns to this theme. Reality may extend beyond observation not accidentally, but structurally. There is also an important scientific humility here. No direct evidence currently confirms that other universes truly exist. Many cosmologists remain skeptical or cautious about strong multiverse claims precisely because observational testing becomes extraordinarily difficult, and that caution matters. Science works best when imagination remains tied carefully to evidence. Still, even without certainty, the multiverse framework reveals something profound about the direction modern cosmology has taken. The universe increasingly appears less like a neatly bounded machine and more like one local expression within a much larger possibility space. A cosmos where reality may unfold differently elsewhere beyond unreachable horizons. And strangely, rather than making our universe feel less meaningful, this perspective can create a deeper sense of fragility and appreciation. Because the existence of stars, planets, oceans, memory, music, sleep, and consciousness may depend on an extraordinarily delicate chain of physical conditions. You're listening tonight inside a universe capable of producing awareness. A universe where ancient stars forged heavy elements, where chemistry assembled living cells, where evolution slowly generated minds capable of wondering about cosmic origins. And perhaps somewhere far beyond our horizon, other realities unfold under entirely different skies, some silent, some chaotic, some empty, and perhaps a few containing beings who also look upward through darkness, wondering whether their own universe is the only one. As the possibility of many cosmic regions slowly settles into the background of thought, it becomes tempting to ask a dangerous question. If other structures or universes truly exist beyond our observable horizon, could their presence ever leave traces inside our own sky? Modern cosmology does not provide a clear answer to that question. Most observations still fit remarkably well within the standard picture of inflation, cosmic expansion, and large-scale structure formation. The universe behaves with extraordinary consistency across enormous distances. Galaxies cluster in predictable ways. Ancient radiation follows patterns inflation anticipated decades before detailed measurements became possible. In many respects, cosmology has been astonishingly successful, and yet, few small irregularities remain, not dramatic enough to overturn established physics, not strong enough to prove hidden universes, but persistent enough to continue quietly attracting attention. One of the most famous examples is the cold spot. Hidden within the cosmic microwave background lies a region slightly colder than surrounding areas across an unusually large patch of sky. The temperature difference itself is tiny, far smaller than anything human skin could notice, yet cosmologically, the scale of the structure appears curious. At first, many scientists assumed it was probably just an ordinary statistical fluctuation. Given enough random variations spread across the sky, unusual regions occasionally appear by chance, and that explanation may still be correct. But over time, astronomers also discovered enormous cosmic voids in the distribution of galaxies roughly aligned with the cold spot's direction. Vast regions where galaxies appear thinner and more sparsely distributed than average. Some researchers propose that light crossing such emptier regions could lose small amounts of energy during its long journey toward Earth, slightly cooling the observed radiation. Others suggested the voids alone may not fully explain the effect, and a few more speculative ideas cautiously considered whether the cold spot might reflect deeper structures connected somehow to inflation or regions beyond the observable universe. Importantly, none of these explanations has achieved universal agreement, and that uncertainty matters, because cosmology becomes dangerous when mystery is treated too eagerly as proof. The universe is subtle. Large datasets naturally contain strange-looking features from time to time. Human minds are remarkably good at detecting patterns, even when those patterns arise accidentally. Still, the cold spot remains emotionally fascinating because it feels like a small imperfection in the otherwise smooth memory of the cosmos. A faint asymmetry resting quietly inside ancient light. Another anomaly became famous partly because of its strangely dramatic nickname, the Axis of Evil. Despite sounding almost mythological, the phrase originally emerged half humorously among physicists studying curious alignments in the larger-scale temperature fluctuations of the cosmic microwave background. Under ordinary assumptions, the early universe should appear statistically random in all directions at sufficiently large scales. No preferred cosmic orientation should stand out strongly, and yet some analyses suggested certain large-scale patterns appeared unusually aligned across the sky. Again, caution is essential here. Many cosmologists suspect these alignments may ultimately result from subtle measurement effects, foreground contamination, statistical coincidence, or the difficulty of extracting tiny signals from enormously complex datasets. Others remain less certain. The anomaly has weakened somewhat under improved analysis over the years, yet discussions continue because the patterns never disappeared completely. What makes such anomalies emotionally intriguing is not necessarily their statistical strength, but the feeling they create. The sense that the universe may contain faint structures almost visible at the edge of understanding, like noticing barely perceptible shapes moving beneath dark water. Not enough to identify clearly, but enough to keep attention lingering quietly. More recently, astronomers studying extremely distant quasars, brilliant galactic cores powered by supermassive black holes, noticed additional large-scale directional irregularities in certain datasets. Some measurements hinted that distant structures may not distribute themselves quite as uniformly as simple models predict. Once again, the scientific situation remains unsettled. Future observations may erase these tensions completely. Improved instruments may reveal hidden systematic errors, or entirely ordinary cosmic variants may explain the apparent asymmetries. And honestly, that outcome would not surprise most cosmologists at all. Science often advances through temporary mysteries that later dissolve naturally. Yet there is still something beautiful about the process itself, the willingness to examine tiny irregularities carefully, to notice subtle deviations, to remain open without surrendering caution. Cosmology exists in a delicate balance between imagination and restraint, too little imagination, and important discoveries remain invisible, too little restraint, and every statistical fluctuation becomes mythology. The healthier science usually lives somewhere in between, patient, careful, curious. This balance becomes especially important when discussing the possibility of structures beyond the observable universe. Could collisions between inflationary bubble universes leave scars in the microwave background? Some theoretical models suggest they might. Could hidden topology imprint repeating signatures across the sky? Possibly. Could unknown large-scale physics subtly influence visible structure? Perhaps. But at present no observation definitively confirms any of these possibilities. And preserving that uncertainty honestly matters far more than manufacturing certainty prematurely. Because one of the deepest lessons cosmology teaches is humility. The observable universe is already almost unimaginably large. The datasets involved contain extraordinary complexity, and human beings are still learning how to interpret patterns stretched across billions of light years and nearly the entire age of the cosmos. Tonight, perhaps the wisest emotional response is neither belief nor dismissal, only quiet attentiveness. The recognition that reality may still contain structures beyond our current understanding, while also accepting that science moves slowly for good reason. The universe has existed for billions upon billions of years. It does not hurry its secrets. Sometimes they emerge only as faint irregularities inside ancient light, small whispers resting softly at the edge of the observable sky. As the faint anomalies hidden in the ancient sky slowly fade back into silence, another realization begins quietly unfolding beneath everything we have explored so far. The universe is not only expanding, its expansion is accelerating. And this discovery changed cosmology forever. For much of the 20th century, astronomers assumed gravity would gradually slow the expansion of the universe over time. After all, gravity pulls matter together. Galaxies attract one another. Clusters form. Stars emerge because matter gathers rather than disperses. So it seemed natural to imagine the universe expanding outward after the Big Bang, while gravity steadily applied the brakes. Perhaps expansion would continue forever, but slow gradually over billions of years. Or perhaps one distant day gravity might finally halt expansion entirely and pull everything back inward. But during the late 1990s, observations of extremely distant exploding stars revealed something astonishing. The expansion of the universe was not slowing down, it was speeding up. Galaxies were drifting apart faster over time. The distances themselves seemed increasingly restless. At first, many scientists were cautious. Extraordinary claims require extraordinary evidence, especially in cosmology, where observations stretch across incomprehensible scales. But as additional measurements accumulated, from supernova observations, galaxy surveys, and the cosmic microwave background, the same conclusion returned again and again. Something was pushing space-time outward, something subtle, vast, and still deeply mysterious. Scientists eventually gave this unknown influence a name: dark energy. The phrase sounds dramatic, almost cinematic, yet in practice it mostly reflects humility. Dark energy simply means that the underlying cause of accelerated expansion remains uncertain. We observe the effect clearly, but its deeper nature is still debated. One possibility is that empty space itself contains a tiny intrinsic energy spread throughout the cosmos. Normally, when people imagine emptiness, they imagine absolute nothingness, complete absence. But quantum physics paints a softer and stranger picture. Even vacuum appears restless, Tiny fluctuations shimmer constantly through empty space at microscopic scales. Fields permeate the universe quietly, even in regions devoid of matter, and if space itself possesses even a minute amount of energy everywhere, then across cosmic distances the effect becomes enormous, not because the energy is intense locally, but because there is so much space. The larger the universe grows, the more space exists, and therefore the more this subtle, expansive effect accumulates across the cosmos. To visualize this gently, imagine dots drawn across an enormous elastic sheet. As the sheet stretches, nearby dots separate slowly while distant dots drift apart increasingly quickly, because more stretching occurs between them. Now imagine the stretching itself gradually intensifying over time. The sheet becomes more eager to expand. The distances themselves become active participants in the motion. This is roughly the emotional intuition behind dark energy. Not a wind pushing galaxies through space, not an explosion throwing matter outward, but space-time itself increasingly stretching on the largest scales. And this expansion creates profound consequences for the future of the universe. At local scales, gravity still dominates. The Earth will continue orbiting the Sun. The Milky Way and nearby galaxies remain gravitationally connected. Stars still form inside clouds of collapsing gas. But across vast intergalactic distances, dark energy slowly wins. Galaxy clusters drift apart. Distant light becomes increasingly redshifted and faint. Cosmic structures gradually separate like boats carried outward across an endlessly widening sea. There is something strangely emotional about realizing that the night sky itself is temporary. Not temporary on human timescales, of course. Humanity will come and go long before these cosmic transformations fully unfold. But on scales of trillions of years, the visible universe will slowly change in profound ways. Galaxies beyond our local gravitational neighbourhood will eventually recede so rapidly that their light can no longer reach us. One by one, distant island universes will fade beyond the cosmic horizon, not destroyed, not extinguished, simply carried too far away by the expansion of space-time itself. Future observers may inherit a dramatically lonelier cosmos. The great tapestry of galaxies currently visible through modern telescopes may disappear almost entirely from view. And perhaps most hauntingly, future civilizations might never possess enough evidence to reconstruct the true history of cosmic expansion at all. The cosmic microwave background will continue stretching toward longer and weaker wavelengths until it becomes almost undetectable. Distant galaxies will vanish beyond visibility. The large-scale structure of the universe will slowly fade from observational reach. Future astronomers, living trillions of years from now inside an isolated galaxy group, might conclude that their local stars represent nearly the entire universe. The evidence of the Big Bang itself may quietly disappear from the sky. There is something deeply melancholic about that possibility. Humanity may exist during a rare era when the universe still remembers its own origins visibly. A brief window when ancient radiation still crosses space. When distant galaxies remain observable. When the large-scale structure of the cosmos can still be mapped before expansion gradually hides it away. And yet dark energy remains profoundly mysterious. Despite all our observations, scientists still do not fully understand why accelerated expansion exists at all. Some possibilities involve vacuum energy. Others suggest subtle modifications to gravity itself on cosmic scales. Still others propose entirely new physical frameworks not yet fully understood. For now, the universe continues expanding quietly, while the deeper cause remains partially hidden. Again and again, cosmology returns us to this same emotional pattern. Observation reveals astonishing truths, and behind those truths waits another layer of mystery. the universe expands, then accelerates, then gradually isolates itself. The visible cosmos slowly thins, galaxies drift outward through growing darkness. And all the while, conscious beings briefly emerge inside one small local region, trying to understand the invisible forces reshaping space-time itself. Tonight, somewhere beyond your own quiet room and sleeping city, the galaxies continue moving apart across incomprehensible distances. Ancient light continues stretching thinner through expanding space, and the universe itself keeps slowly opening wider, while at the same time becoming lonelier. As the slow expansion of the universe continues quietly outward through the imagination, it becomes possible to picture a future sky unlike anything humanity has ever known. Not violent, not explosive, not filled with cosmic catastrophe, but empty. At first, the idea sounds almost impossible to believe because the modern night sky already feels ancient and permanent. Galaxies drift across telescope images like glowing rivers. Nebulae bloom softly through darkness. The Milky Way arches overhead as though it has always existed and always will. Yet cosmology tells a gentler and stranger story. The visible richness of the universe is temporary. Over unimaginable stretches of time, dark energy will continue widening the distances between cosmic structures. Galaxies beyond our local group will drift farther and farther away, until eventually their light can no longer reach future observers at all. One by one, the distant lights will disappear, not because the galaxies themselves vanish, but because space expands too quickly between them. It is difficult not to feel something emotional in that realization. Tonight, when modern telescopes gaze outward, they see billions of galaxies scattered across the observable universe. Some appear as elegant spirals, others glow as massive elliptical swarms of stars. Clusters and filaments weave together into enormous cosmic structures stretching across distances almost impossible to emotionally comprehend. Future civilizations may see none of this. In the unimaginably distant future, observers living inside our merged local galaxy group may look outward and find only darkness beyond their immediate cosmic neighborhood. The larger universe will still exist, but its light will no longer arrive. Imagine living in a vast library while, slowly and silently, the books begin disappearing one by one from the shelves. Not burned, not destroyed, simply carried farther away through endless hallways until they can no longer be reached. At first, only distant shelves vanish, then entire rooms, then whole wings of the library fade into darkness. Eventually, only a small local collection remains visible. The future cosmos may evolve in something like this way. And perhaps even stranger. The evidence of cosmic expansion itself may gradually disappear. Right now, astronomers know the universe expands because they can observe distant galaxies receding across enormous scales. They can measure redshift. They can map large-scale structure. They can study the cosmic microwave background, the ancient radiation left behind by the early universe. But trillions of years from now, much of this evidence may no longer be accessible. The cosmic microwave background itself continues stretching as space expands. Its wavelengths gradually lengthen until the radiation becomes so weak and diffuse that future civilizations may never detect it. The oldest visible memory of the Big Bang will slowly fade into near invisibility. Meanwhile, galaxies beyond the local gravitationally bound group will disappear across the event horizon one after another. Future astronomers may inherit a universe appearing static, isolated and eternal. They may conclude that their galaxy alone constitutes most of existence. The observable clues pointing toward cosmic expansion and a primordial beginning could vanish almost completely from the sky. There is something hauntingly beautiful about this possibility. Humanity may live during one of the few eras in cosmic history when the large-scale universe remains visible enough to understand. A narrow observational window suspended between two different darknesses. In the beginning, the universe was too hot and opaque for light to travel freely. The early cosmos concealed itself behind glowing plasma fog. Then came billions of years during which galaxies, stars, and ancient radiation became visible across expanding space. And eventually, the universe may grow so large and isolated that much of that evidence disappears once again. Cosmic knowledge itself may depend on timing. This realization changes the emotional feeling of astronomy. The night sky is not merely scenery, it is information. A temporary archive of ancient light crossing spacetime before expansion gradually carries it away forever. Every galaxy image captured by telescopes today is part of a fleeting era of visibility, and somehow conscious beings evolved during exactly this period. There's something almost improbable about that. The universe became transparent, stars formed, heavy elements emerged from stellar furnaces, planets cooled, life evolved, consciousness appeared, and all of it happened early enough in cosmic history for observers to still witness the large-scale structure of the universe before dark energy erased much of the evidence. Some cosmologists describe this as a kind of observational privilege, not privilege in a moral sense, but in a temporal one. We exist during a cosmologically fortunate age, late enough for complexity to emerge, early enough for the universe to remain observable, and perhaps this is one reason cosmology often feels emotionally different from other sciences. There is a quiet fragility running beneath it, a sense that the visible universe itself is temporary. The galaxies overhead tonight are not permanent companions. They are travellers crossing a brief window of mutual visibility before cosmic expansion slowly separates them forever. Even the Milky Way will eventually change profoundly. Over billions of years it will merge with the Andromeda Galaxy, forming a larger combined structure drifting through increasing darkness while the wider universe fades beyond reach. Stars themselves will gradually die across immense timescales. New star formation will slow. Ancient stellar remnants will linger through colder cosmic ages. The universe will not end suddenly. It will thin, quietly, slowly, like embers fading after an enormous fire. And yet, despite the melancholy hidden inside this future, there is also something strangely peaceful about it. Because even in a fading cosmos, the universe continues unfolding according to deep underlying structure. Expansion, gravity, light, causality, all continue shaping reality with immense consistency across time. The cosmos does not panic as it changes, it simply evolves. Galaxies drift apart, ancient radiation cools, visibility narrows, and inside one brief era of light and structure, conscious beings ask questions about the larger darkness surrounding them. Tonight, perhaps the night sky feels a little different now, not smaller, but more temporary. A vast cosmic archive still open for a short while longer before the distant pages slowly disappear into expanding silence. As the image of a slowly darkening future cosmos settles gently into silence, attention naturally begins shifting inward toward the meaning of the boundaries themselves. All throughout this journey, the universe has repeatedly revealed the same strange pattern. Every time humanity extended its vision farther outward, another horizon appeared. We discovered galaxies beyond the Milky Way, then horizons beyond galaxies, then inflation beyond the observable universe, then possible structures beyond inflation itself. Again and again, the visible cosmos opened wider, and yet complete visibility remained just out of reach. It is tempting to think of these horizons as unfortunate obstacles, barriers frustrating scientific progress, cosmic curtains preventing us from seeing the full structure of reality. But modern physics quietly suggests something deeper. The boundaries may not be accidents, they may be part of the architecture of the universe itself. To understand this gently, it helps to return to one simple idea. Information does not move infinitely fast. Every observation depends on signals travelling through space-time. Light carries information across darkness. Gravity influences matter through causal relationships unfolding over time. Even memory inside the human brain depends on physical processes transferring information between neurons. Reality unfolds through communication, and once space-time itself begins expanding rapidly enough, some regions become permanently separated from one another's information. This is what cosmic horizons truly represent. Not walls of matter, not edges of existence, but limits on causal connection, limits on which parts of the universe can meaningfully interact. There's something profoundly philosophical hidden inside this realization, because it means the observable universe is not simply the universe we happen to see. It is the universe capable of participating in our causal history, a relationship rather than a location, and perhaps even more strangely, modern theoretical physics increasingly hints that information itself may play a deeper role in reality than scientists once imagined. Some ideas emerging from black hole physics suggest that horizons may contain hidden informational properties. Black holes, for example, do not appear to erase information completely as once feared. Instead, many physicists suspect information becomes encoded in subtle ways along boundaries surrounding these extreme objects. This led toward one of the strangest conceptual developments in modern theoretical physics: the possibility that boundaries themselves may carry profound descriptions of physical reality. The holographic principle emerged partly from this line of thinking. The phrase sounds highly technical at first, but the emotional intuition underneath can be approached softly. A normal hologram stores three-dimensional visual information on a two-dimensional surface. In a somewhat analogous way, certain theories suggest that information about a region of space-time may somehow relate to structures encoded along its boundaries. Importantly, physicists are still exploring what this truly means. The mathematics behind holography becomes extremely advanced very quickly, and many questions remain unresolved. But emotionally, the idea is extraordinary. The boundaries of reality may matter more deeply than we once assumed. Horizons are not merely places where vision stops. They may be active features of how information itself behaves in the universe. And this connects beautifully back to everything we have explored tonight. Inflation created horizons. Dark energy enlarges them. Causality defines them. Observation depends on them. The observable universe itself emerges because information requires time to travel across expanding space-time. Again and again, the universe appears less like an unlimited open container, and more like a layered structure of relationships. Some regions remain connected, others drift permanently apart. Knowledge itself becomes local. There is something deeply humbling about this. For centuries, science progressed partly through the assumption that enough patience and technology would eventually reveal everything: build larger telescopes, construct faster computers, gather more data, extend observation farther outward, and certainly those efforts transformed human understanding beyond anything earlier civilizations could imagine. Yet cosmology now raises a quieter possibility. Some aspects of reality may remain permanently inaccessible, not because science failed, but because the universe itself imposes limits on observation. Even perfect instruments cannot see beyond certain causal horizons. even infinite patience cannot recover light that will never arrive. The equations describing space-time quietly contain their own boundaries. And perhaps this is why cosmology often feels emotionally different from ordinary astronomy. It is not merely the study of distant objects, it is also the study of the limits of perspective itself. The realization that every observer exists inside a finite informational bubble, surrounded by larger unseen structure. And yet, strangely, this does not make the universe feel meaningless. If anything, it makes existence feel more intimate. Because consciousness emerges inside these local islands of causality and still manages to reconstruct astonishing truths about the larger cosmos. Human beings discovered the age of the universe while trapped on one small planet. They inferred inflation from faint temperature ripples spread across ancient radiation. They detected the acceleration of cosmic expansion using tiny variations in distant starlight. From inside one local bubble of visibility, the universe began understanding its own large-scale structure through conscious minds. There is something beautiful in that. Perhaps complete knowledge was never required for wonder. Perhaps horizons themselves are part of what gives the cosmos emotional depth. A universe entirely transparent might feel strangely flat and exhausted, but instead, reality stretches outward beyond visibility, beyond certainty, beyond complete comprehension, and somewhere beyond every horizon tonight, the rest of existence continues unfolding silently. As the boundaries of the observable universe slowly settle into stillness, one final realization remains waiting quietly beneath everything we have explored tonight. For all the vastness of the cosmos, for all the hidden regions beyond our horizon, for all the unreachable galaxies and invisible structures drifting forever outside our causal reach, the universe still produced something extraordinary. It produced observers. Somewhere inside this immense, expanding cosmos, matter gathered itself into stars. Stars forged heavier elements deep inside their burning cores. Those elements scattered outward across space, later becoming planets, oceans, atmospheres, and eventually living cells. And after billions upon billions of years of cosmic evolution, the universe became capable of asking questions about itself. That may be one of the strangest facts modern science has ever revealed. Because consciousness did not appear outside the universe looking inward. It emerged from within the universe itself. Every thought you have ever experienced, every memory, every dream, every quiet moment of wonder beneath a night sky, arose from atoms forged inside ancient stars drifting through an evolving cosmos. You are not separate from the universe observing it. You are one local expression of the universe becoming aware of its own existence. There is something profoundly calming about that realization when approached slowly. Human beings often feel small beneath cosmic scale, and in one sense, we truly are small. Earth is tiny compared to galaxies. Galaxies are tiny compared to the observable universe. The observable universe itself may be only one local patch within a vastly larger reality extending beyond all visibility. And yet scale alone does not determine significance. A single conscious mind can contain reflections about the entire cosmos. Tiny biological organisms living on a small planet discovered the age of stars, the expansion of space-time, the existence of black holes, and the faint radiation left behind by the early universe. From inside one fragile world orbiting one ordinary star, the universe began reconstructing its own history. Not perfectly, not completely, but astonishingly far. And perhaps this makes the observable universe feel different emotionally once more. Earlier tonight, the observable universe may have seemed limiting, a reminder that most of reality lies permanently beyond our reach. But now, perhaps it can also be seen as something else. A window, not a prison, not a failure of knowledge, but a local opening through which the cosmos became visible to itself. Every observer inhabits such a window, a finite region shaped by causality, light, and expansion. And inside those temporary windows, awareness briefly appears. The universe may never become fully knowable from any single perspective. Horizons prevent complete visibility. Expansion isolates distant regions. Information itself travels with finite speed through evolving spacetime. Yet even within those limitations, extraordinary understanding became possible. That balance between mystery and knowledge may be part of what gives cosmology its emotional beauty. We learned enough to realize how much remains hidden, enough to understand that the observable universe is not the whole cosmos, enough to infer inflation from ancient ripples in radiation, enough to detect dark energy reshaping the future of space-time itself, enough to recognize that the night sky is not static scenery, but a temporary archive of ancient light crossing expanding space, and perhaps most remarkably, enough to recognize the limits of our own perspective. Science did not merely reveal the universe, it also revealed the boundaries built into observation itself. There is a quiet maturity in that realization. The deepest scientific understanding does not always lead towards certainty. Sometimes it leads toward humility, toward the recognition that reality may always remain larger than any model describing it. And yet that uncertainty does not erase meaning. If anything, it deepens wonder. Because the universe did not owe us visibility at all. It did not owe us stable stars, transparent space, long-lived galaxies, or conscious minds capable of reflection. And still, here we are, living during a brief cosmological era when ancient radiation still fills the sky, when distant galaxies remain visible, when the large-scale structure of the cosmos can still be studied before dark energy slowly carries much of it away. You exist during one small illuminated chapter in the life of the universe, a chapter where reality has not completely hidden itself yet. There is something peaceful in imagining all of this unfolding together tonight. Beyond your room, Earth continues turning quietly beneath the atmosphere. Beyond Earth, the moon circles patiently through darkness. Beyond the solar system, stars drift through the Milky Way. Beyond the Milky Way, galaxies continue separating across expanding space-time. And farther still, beyond every visible horizon, beyond every reachable signal, the rest of reality continues unfolding silently, in directions no observer may ever fully witness. Perhaps other conscious beings exist somewhere beyond our horizon tonight. Perhaps not. Perhaps entirely different cosmic regions drift endlessly beyond our reach. Perhaps space-time itself loops back into structures larger than visibility allows. Perhaps inflation still continues elsewhere beyond the observable universe. Much remains uncertain, but one thing appears beautifully clear. The universe is not empty. It is filled with structure, memory, light, causality, and awareness. And within one small region of that immense unfolding process, conscious beings learn to look outward and ask where the boundaries came from. Maybe that is enough. Not complete certainty, not total understanding, just the quiet miracle that a universe filled mostly with darkness and expanding emptiness became capable, at least briefly, of contemplating its own hidden shape. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already drifting somewhere between waking and dreaming, thank you for spending this quiet stretch of cosmic time here with me. If these gentle journeys into science and mystery bring you some peace, you're always welcome to return for another slow exploration of the universe together. For now, the observable universe remains around you like a softly glowing window suspended in darkness. Beyond that window, reality may continue far beyond visibility, larger, stranger, and quieter than human imagination can fully hold. And somewhere within it all, the universe became aware enough to wonder, sleep peacefully, wherever and whenever you may be.